Hello, my name is Jim Olson, and this is a video on the M2I2 method of graphing. When I took calculus, I learned this method. I found the M2I2 ACIDS method of graphing very useful for me as a student, and now I'd like to share it with you. In this video, I'm going to be graphing these 5 examples. This works for polynomials. This works for rational functions. It could also be used for other functions, but I think I'll just do these in this particular video. When you're asked to graph a function in a calculus class, the following is a good list of aspects to consider. M2 means maximum and minimum points. I2 is intercepts and inflection points. A is asymptotes. C is concavity. ID is increasing and decreasing. And S is symmetry. Let me make a quick comment about graphing. We're not graphing in order to get a graph, because if we want a graph, we can just have a graphing calculator or Desmos or something like that graph it for us. The reason we're doing this by hand is to get an understanding of how derivatives work, how they give us information about the graph, and understanding the relationship between aspects of the graph. This is a brief list. Also in this video, I'm going to be sharing a couple extra tips on graphing. In more detail, here are the questions we're going to be asking. On the graph, where are the maximum and minimum points? What are the x and y intercepts? What are the inflection points? Where are the vertical and horizontal asymptotes? That is, what is the end behavior? Where is the curve concave up? Where is the curve concave down? Where are the function values increasing and where are they decreasing? And does the graph have symmetry? Equivalently, is the graph even or odd? In this video, I'm going to be moving through the ideas fairly quickly so that you can see the interplay. If you need an introduction to derivatives, you might want to look in a calculus book or look at a different video. My goal is to see how all these aspects fit together. I am going to be using an OpenStax book, which is an open source book available on the internet. And here's a picture of it. Maybe I'll take a quick peek at it for you. Here's the front of the book, and it's pretty easy to navigate. You can hit table of contents over here and work your way through the book. The first thing I'd like to look at is maximum and minimum points. And one way to find maximum and minimum points is using the first derivative test. The key is that the derivative is changing sign. The derivative is going from positive to negative, or it's going from negative to positive. And I'd like to show this on GeoGebra. The first derivative test is a pretty easy test to understand. This is a maximum point. If we look at our derivative, which is the slope of the tangent line, the derivative right here is 1.72. And it's positive here on the left because the function values are increasing. And then as we get to this point, on the other side of the maximum point, we have a negative derivative. The function values are decreasing. So a maximum occurs when the derivative goes from positive to negative. In a similar manner, moving from left to right, if the slope of the tangent line goes from negative to positive, In other words, the derivative is going from negative to positive. That means we have a minimum point. This is the first derivative test. Now for concavity. To determine concavity, we're going to be using the second derivative. If f double prime is positive, it's concave up. If f double prime is negative, it's concave down. We could say much more about concavity, but I'll leave that for another video. So maybe I'll show you just a few pages from the OpenStax book in case you'd like to see more details. A critical number in calculus is a value in the domain for which the derivative is 0 or the derivative is undefined. And then c comma f of c is called a critical point. Here is the first derivative test, talking about the derivative changing from a positive to a negative to a positive, or the derivative staying the same. Here is the second derivative test. The second derivative test is used when you have the second derivative. The first derivative is 0. When the second derivative is positive, we have a local minimum. When the second derivative is negative, we have a local maximum. If both the first and second derivatives are 0, the test is inconclusive. Here is the test for concavity. Now let's talk about finding intercepts. The way we find intercepts is the same, whether it's Algebra 1, Algebra 2, or Calculus 3. To find y-intercepts, substitute 0 for x and solve for y. To find x-intercepts, substitute 0 for y and solve for x. You might ask why. The reason is all the points on this y-axis have x equals 0. We haven't moved to the left or to the right. Conversely, all points on the x-axis have not moved up or down. The y value is 0. So now we're ready to do our first example. And I'm going to switch over to my Epic Cam so I can write this out. You may need to pause the video from time to time. I'll leave that up to you. I think I'm going to do a couple of these on graph paper and a couple of these just on notebook paper. So now I'll be switching to the camera. So here is our polynomial. Oftentimes I start with symmetry, but I think I'm going to leave symmetry for the end. This one does not have symmetry. So let's talk about intercepts. The easy intercept is going to be when we substitute 0 in for x. And that is going to give us 0 for x and 12 for y. So this is the y-intercept. On the other hand, if we substitute 0 in for y, I get this equation. By the way, this equation is different than this equation. This is the function with y over here, and this has 0. So this is going to require us to factor this. And I won't be covering synthetic division in this video, but we would need to have a way of factoring this. So let's just write down the factoring from, work on another piece of scratch. So I have x minus 2 times x minus 2. This factor appears twice, and x plus 3. When I set these equal to 0, I get -3 over here and I get positive 2 over here. This is what's called a double root. And this is going to be behaving a little bit different than this one. So we have 2, 0, and -3, 0 for my x-intercepts. So let's go ahead and get a graph started. Might want to use a ruler, but maybe I'll just freehand it here. So we have 2, 0. And we have -3, 0. We have a point up here at 0, 12. I'm not sure how high it's going to go, so I think I'm going to wait before I label my y-axis. Okay, so now we're ready to start taking some derivatives. So let's calculate the derivatives. The derivative is 3x squared minus 2x minus 8, and we are going to set that equal to 0. And we are going to factor this. And when we set this equal to 0, we get x equals -4/3. And this factor equal to 0 gives x equals 2. These are going to be the critical values. Let's get the second derivative. Here's the second derivative. Now, when we substitute, we're going to be substituting this critical value into the second derivative, and we're going to be substituting it into the original function. Let's go ahead and substitute it into the original function. So we're going to get -4/3 for the input. And let's now calculate using a calculator the output. I'm getting 18.5 from my calculator. Now let's do the same thing with 2, substituting 2 into the original function. I'm getting 2, 0. So this 2, 0 is not only an x-intercept, but it is also going to be an extreme point. Now, we might be able to see that this is going to be a maximum and this is going to be a minimum. But just to check, if we take y prime or y double prime and we substitute in 2, x equals 2, we get 12 minus 2, which is 10. And since that is positive, this is going to be a minimum point. This is a minimum point. And similarly, we could plug in a -4/3 in here, and that's going to give us a negative value, which means this is a maximum point. So I have found my maximum and minimum points. And I think now that I know the top point, I can go ahead and graph this. So let's go ahead and get our y-intercept on here, 5, 10. This is here at 12. And my maximum point is at -1 1/3, 18.5. -4/3, 18.5. So we're pretty well done with this, but we don't have the inflection point yet, and we haven't looked at the end behavior. The end behavior is when x is approaching positive infinity and x is approaching negative infinity. When x goes to positive infinity, this term is going to be dominating, and a big positive cubed is going to be a big positive. So this is going to be going up. On the other hand, if it's negative, a negative to an odd power will be negative, and this is going to be coming down in this direction. Now, the thing I'd like to emphasize next is the difference between these two intercepts. This intercept was from a factor that was to an odd power, which means the graph is going to be cutting through that point. The 2 is from a factor that was to an even power. So it's probably going to be not only an intercept, but also a max or min point. So this is going to be coming like this. The only thing we need to do now is find the inflection point. So let's calculate the inflection point. To calculate the inflection point, we set the second derivative equal to 0. My second derivative is here, and I'm going to solve this. X is 2/6, which is 1/3. And now I'm going to be substituting 1/3 into the original function to get the corresponding y value, and I have 1/3, comma, 9.259. So this is the inflection point. And that's going to be right about here. 1/3, comma, 9.3. And now I can graph the rest of this here. And here's my graph for number 1. If you need more points or you need a more accurate graph, then use technology. Let's move now to the second example. This is our second example. It's a rational function, 2x plus 3 over x minus 4. Let's begin with intercepts. If my input is 0, this is 0 and this is 0, I get 3 over negative 4, and we get the ordered pair 0, comma, negative 3/4. This is the y-intercept. If y equals 0, I get 0 equals to the fraction. Now, how do you make a fraction 0? In order to make a fraction 0, the numerator must be 0. So we have 0 equals 2x plus 3, and we solve this, and we get negative 3/2. So let's write the ordered pair for the x-intercept. Now let's calculate the first and second derivative. We're going to need to use the quotient rule. The first derivative is negative 11 over x minus 4 quantity squared. Now let's do the second derivative. Here is the second derivative. If we set the first derivative equal to 0, we want the numerator to be 0, but you can never make the numerator 0. So this does not have a place where the derivative is 0, which means there's not going to be a max or min point. No max or min points. Similarly, but somewhat different, if we put the second derivative equal to 0, 22 is never 0, so this has no inflection points. So let's take inventory. M2, max min points, we've done that. Intercepts, we've done that. Inflection points, we've done that. Now, asymptotes. Let me switch back to the slides to talk about inflection points. Inflection points occur when the concavity changes from concave up to concave down or vice versa. Inflection points occur when the second derivative is 0 and it changes sign. Now let's talk about asymptotes. Vertical asymptotes occur when the denominator is 0. This is going to be undefined because you can't divide by 0. Horizontal asymptotes are a little different. These occur at end behavior. That is when x approaches positive infinity or negative infinity. So let's take a look in our example at the vertical asymptotes and set the denominator equal to 0. So I'd like to calculate the vertical asymptote. All we have to do is take the denominator equal to 0 and I get x equals 4. X equals 4 is a line. It's a vertical line, and we're going to be putting that on our graph as a dotted line. So let's see if we can get the graph started. Okay, so the y-intercept is here at -3/4, not quite -1. The x-intercept is -1.5. Here's -1, here's -1.5. I have a vertical asymptote at x equals 4. 1, 2, 3, 4. So I'm going to put a dotted line there. There's the vertical asymptote. Now, what about the horizontal asymptote? The horizontal asymptote, we're going to consider the end behavior. That is, we're going to take the limit as x goes to infinity. As x goes to infinity, this 2x term is going to be dominating in the numerator, and the x term is going to be dominating in the denominator. For example, if you put in 1,000, this is 2,000 and change, and this is near 1,000. 2,000 over 1,000 is basically 2 over 1, which is 2. This limit is 2. And this is a y value, so the horizontal asymptote is 2. In a similar manner, if x goes to negative infinity, I also get 2. Let's put this on our graph. Now let's talk about what this means here and what's happening near this. Certainly we cannot put in 4. But if we put in something a little bit to the right of 4, like 4.1 or 4 and 1/100th, if we put 4 and 1/10th, the denominator is going to be small positive 1/10th, and the numerator is going to be somewhere around 11. 11 divided by something tiny, positive divided by positive, is large positive. On the other hand, if we're a little bit to the left of x equals 4, let's say 3.9, if we put 3.9 in, now we're getting negative 1/10, but we're still getting about 11 up here. A positive divided by a tiny negative is a big negative, and this is going to be going down here. So from experience, I know that this graph is going to be going basically like this and approaching this horizontal asymptote. This is going to be concave down because we have a negative value here. Sorry, that's not correct. The reason it's concave down is because of the second derivative. To the left of 4, this is a negative in the denominator, which makes this negative, which makes it concave down. On the other hand, When x is greater than 4, we have a positive down here. A positive divided by a positive is a positive. That's a positive second derivative, so it's concave up. So the rest of my graph is here. It would be nice to get 1 point here. So let's find f of 5, for example, on a calculator. Plugging in 5, I'm going to get 10 plus 3 on the top and 1 on the bottom. I believe that's 13. So we have the ordered pair 5, 13. Let's graph that point. So here's 5, 13. It might be nice to have one more point. I did a calculator and I got 8, 4.75. So this gives me enough to finish my graph. This is getting closer and closer to this horizontal asymptote of y equals 2. So let's write that on our paper. We have a vertical asymptote of x equals 4 and a horizontal asymptote of y equals 2. Maybe just one more comment on number 2. This derivative is negative all the time because of this here. It's a negative divided by a positive. The function is decreasing everywhere. Now let's go to the third example. The third example is g of x is equal to x plus 4 over x squared plus 6x plus 9. Right off the bat, I'm going to talk about the horizontal asymptote. If we take the limit as x approaches infinity here, this x squared is going to dominate not only the denominator, but it's also going to dominate the entire fraction. Like if I put in 1,000, this is going to be 1,000 and change. 1,000 squared is 1,000,000. 1,000 divided by 1,000,000 is something tiny. So the horizontal asymptote in this case is y equals 0. I think I have summarized that on a slide. Sorry about that. I don't think I was sharing the correct screen here. Let me say that again. X squared is dominating the entire fraction here. So this is going to 0. The limit as x approaches infinity is 0. So our horizontal asymptote is x equals 0. In our next example, the numerator is going to be dominating. So that's our horizontal asymptote. While we're on asymptotes, let's do the vertical asymptotes, which means we're going to be setting the denominator equal to 0. And when we factor this, we get x plus 3 quantity squared equals 0. We get x equals -3 for our vertical asymptote. Now let's do intercepts. The x-intercept, we're going to set y equal to 0, which means the numerator needs to be 0. So we get -4, 0. To do the y-intercept, we put 0 in for x and we get 4/9. X is 0, y is 4/9. So we have our intercepts. Now we need the first and second derivative so we can find our maximum points, our minimum points, concavity, and inflection points. So I'm going to do the quotient rule over on a piece of scratch paper. The first derivative is the opposite of x minus 5 over x plus 3 quantity cubed. It was quantity squared to begin with. And the second derivative from the quotient rule again is 2x plus 12 over x plus 3 to the fourth. Setting the first derivative equal to 0 means the numerator is equal to 0. And we get x equals 5. That's our critical value. And then when we substitute in here, in the original function, it looks like we have 9 on the top, 25 plus 30 plus 9 on the bottom. So we have, from a calculator, negative 1/4, pretty small. Now, we need to determine if this is a maximum point or a minimum point. So we're going to use the second derivative test. I'm going to take the second derivative and I'm going to be substituting in 5. Let's run that into a calculator and see what we get. When I substitute 5, my critical value, into the second derivative, I get a positive number. It happens to be tiny, but it's positive, which means by the second derivative test that this is a minimum point. That is the only extreme point. So we've done maximum and minimum points, we've done intercepts. Now let's do the inflection point. To calculate the inflection point, we're going to set the second derivative equal to 0. To make a fraction 0, we need the numerator to be 0. 2x equals negative 12, so we have x equals negative 6. Now we need the output, so let's substitute 6 into our original function with a calculator. We get negative 2/9. So the inflection point is negative 6, negative 2/9. All right, so now let's make our graph. So our y-intercept is 0,4/9, a little bit less than 1/2. We have a vertical asymptote here at negative 3. A dotted line here at negative 3. Now let's see what's occurring on either side. Remember, this denominator here is x plus 3 quantity squared. So if, let's say I'm a little to the left of negative 3, maybe negative 3.1. Negative 3.1, when you plug that in here, I'm going to get a negative, but when I square it, it's going to be positive. Negative 3.1 plus 4 is going to be positive. It's going to be positive divided by a positive. In fact, a number divided by something tiny, this is going to be shooting up to positive infinity. In a similar manner this time, if I'm at negative 2.9, negative 2.9 in here is 0.1. 0.1 is squared is positive again, positive divided by positive. So it's going up on both sides of the asymptote. On our previous example, it went to infinity, positive infinity on one side and negative infinity on the other side. This one's different because my factor was squared. What else do we have? We have an x-intercept of -4. We have a minimum at -5, -1/4. So there's our minimum point. And we have an inflection point over here. So what's happening is this is going to 0 because we have a horizontal asymptote here at y = 0. This is getting smaller and smaller to 0, and this is shooting up, getting closer and closer. This is coming down. It's coming through this point. It's hitting a negative here. It's concave up until it gets to -6, and then it's concave down as it approaches 0. Here are my intercepts. Here's my minimum point. Here's my inflection point. Let's take a sip of coffee and move to example 4. Example 4 is similar to the last example. However, the numerator now has a higher degree than the denominator. So the numerator is going to be dominating, and this is not going to have a horizontal asymptote. Let me summarize horizontal asymptotes. You consider the degree of the numerator and the degree of the denominator. If the degrees are equal, then we have a horizontal asymptote. We look at the coefficients of the highest degree terms, and we have y equals that number. If the degree of the numerator is smaller than the degree of the denominator is going to dominate and it's going to go to 0. Y = 0 is our horizontal asymptote. However, if the degree of the numerator is 1 more than the degree of the denominator, we do not have a horizontal asymptote, but we do have a slant asymptote. The equation of the line can be found by dividing out and taking the limit as x approaches positive infinity. Now let's work out the 4th example. Okay, once again, we're going to need to set the numerator equal to 0 and the denominator equal to 0. This is x minus 3 times x minus 3. So to find our y-intercept, x is going to equal 0. This term is 0, this term is 0, this term is 0. 9 divided by 2 is 4.5. This is my y-intercept. For my x-intercept, y is equal to 0, which means the numerator is equal to 0, which means x is equal to 3. So we have 3, 0 is my x-intercept. Now let's do the derivatives with the quotient rule. My first derivative is here, x squared plus 4x minus 21 over x plus 2 quantity squared. My second derivative is here. I need to factor this numerator. This is x plus 7 times x minus 3. If we're looking for our max-min points, we set that numerator equal to 0, and we get -7 and its function value, and +3 and its function value. Well, we already saw the 3, so this point 3, 0 is an x-intercept and it's a max-min value. If you substitute -7 in here from a calculator, we get -20. When I put +3 into my second derivative, I get a positive divided by a positive. The second derivative with 3 plugged in is positive, which means this is concave up. This is a minimum point. On the other hand, if you substitute -7 in to the second derivative, -7 plus 2 is -5. -5 cubed is a negative. Positive divided by a negative is a negative. This is a negative, which means it's concave down, which means this is a maximum point. Now let's take a look at asymptotes. -2 is the bad value. X equals -2 is the vertical asymptote. We see that when x is going to infinity, the numerator is dominating. So we are not going to be getting a horizontal asymptote. Let me go ahead and do the long division to get the slant asymptote. So my quotient here is x minus 8 plus this fraction. When x goes to infinity, this will drop out. So y equals x minus 8 is the slant asymptote. So I think we're ready to make our graph. So let's start with our intercepts. 0, 4.5. Three, 0. We have a vertical asymptote. Let's see where that is on the sheet here. It is x equals -2. Let me get that dotted line in. So on this side, it's going to be going to positive infinity. So this has a minimum here at 3 and shoots up on an angle that way. We're going to have another curve down here. The maximum point was -7, -20. So way down here at -7, -20, we have a max value. A little bit to the left of -2 here, like -2.1. We're getting a big negative. Because this will be positive divided by a negative. So this graph is going to hit a maximum here and come shooting down on an angle this way. Once again, if we wanted more points, we could get those from a calculator. We didn't do inflection points. What about inflection points? We get inflection points by setting the second derivative equal to 0. If you set this equal to 0, you get 50 equals 0, which is not possible. So there are no inflection points. And now we're ready for our final example, which is a polynomial. And the reason I'm doing this one is because this one does have symmetry. So let's talk about symmetry. If f of x is the same as f with the opposite of x plugged in, which is kind of rare, but it can happen, then f is said to be an even function, and it's symmetric about the y-axis. In other words, plugging in, for example, 5 gives you the same function value as plugging in -5. It has y-axis symmetry. On the other hand, if plugging in the opposite of x is the opposite of f of x, this is an odd function, and it is symmetric about the origin. In other words, 180-degree rotational symmetry. The nice thing about polynomial functions and rational functions, you can look at the powers on x. If all the exponents are even, it means it's an even function. If all the exponents are odd, it is an odd function. And that is what we have here. This is x to the 4th. This is x to the 2nd. And actually, the constant is 9 times x to the 0. This is an even function. So let's switch over to the camera and graph this function. This is an even function. So everything to the right of the x-axis will be mirrored to the left of the x-axis. If we set the original function equal to 0 and factor, I did pick one that factors nicely. This factor gives me plus or minus 3, comma 0, and this one does not give me any. So there are going to be 2 x-intercepts. These are the x-intercepts. For the y-intercept, we get -9. Now let's calculate the derivatives. If we set the first derivative equal to 0, we can factor out a 4x, and we have 4x times the quantity x squared minus 4. So we have 4x times x minus 2 times x plus 2. So we're actually getting 3 critical values, 0, 2, and -2. Now we need to substitute these values into the original equation in order to get the output. Let's do that. And we get 0, -9, which we've already seen. 2, -25, and -2, -25. There's our evenness. There's our symmetry coming in. If you substitute 0 into the second derivative, we get a negative, which means it's concave down, which means this is a max. If we substitute +2 into the second derivative. 4 times 12 is 48, minus 16 is positive, which means it's concave up. This is a minimum, and similarly, this is a minimum. Now let's find inflection points. Putting the second derivative equal to 0, and taking the square root of both sides, and using a calculator, we get these values. This is from the second derivative equal to 0. So these are going to be the inflection points. And let's substitute in to get the y value in the original equation. And we get negative 1.1 and negative 17.9. Sorry, I'm being a little inconsistent on my rounding. I'm rushing a little bit. So now we're ready to make the graph. I see that I have small values of x, but I have some big negative values for y. So I don't think I'm going to use the same scale. I think I'm going to have 2 squares of my graph paper be 1 on the x-axis. And on the y-axis, I think each square is going to be 1. So here's negative 1, 2, 3, 4. Here's negative 5, and so on. Okay, so let's get the points in here. We have symmetry, so every time we have a point on the right, we can have a point on the left. The y-intercept is at negative 9. Two comma negative 25, negative 2 comma negative 25. And our inflection points aren't quite as nice, but we'll put them on here a little bit to the right of 1 and almost negative 18. So this was negative 10, negative 15, 16, 17, 18. About right there. And symmetrically, negative 1.1, negative almost 18. So the concavity is changing there. When x approaches positive infinity, this goes to positive infinity. Since this is an even power, when x goes to negative infinity, it will also be going up to positive infinity. So let me see if I can draw in the graph now. And here's our graph. It's increasing here where we have a positive derivative, and over here where we have a positive derivative. It's decreasing here where we have a negative derivative, and here where we have a negative derivative. It's concave up here in this region to the left of this. It's concave up to the right of this, and it's concave down here. This has been a video on M2I2 ACIDS. This is a list that helps us remember the various aspects we can combine to make a graph. This has been a video on the M2I2 method of graphing with emphasis on rational functions. On YouTube, I'm Dr. O314. Have a great day.